Good afternoon to everyone. So, we are back into our lecture series on advanced hydraulics, and we are in the module 2 discussing on uniform flows. In the last class, we discussed on how to compute flood discharge using uniform flow approximations. We also discussed on the slope area method for computing flood discharge. We also discussed on how to give uniform flow approximations for overland surface flow, where overland sheet flows and all are witnessed. So, today we will discuss on design of channels for uniform flows. The books we are going to refer in this chapter, especially it is Venti Chow's Open Channel Hydraulics and K. Subramania's Flow in Open Channels. What are the channels that are to be designed for uniform flows? As we mentioned in this chapter, we are going to discuss on design of channels for uniform flow. What are the general channel type of channels you witness, or where you encounter, where you would require to design channels for uniform flow? Some of the things are non-erodible channels. How to design non-erodible channels for uniform flow. Then next is how to design erodible channels for uniform flow, and subsequently how to design grass channels for uniform flow. So, we will see all these things partially, not in quite a large extent, but we will see as per our limit and all, as per the course duration and all, we will see as some of the things aspects for the design criteria of these channels. So, what is meant by non-erodible channels? So, the channels that do not allow scour or it do not allow seepage through its bed and through the sides, such channels are called non-erodible channels. Generally, you used to line the channels in the channel beds as well as on the sides, you line it with certain materials, so as to avoid these properties. Erodible channels, the channels that partially scour. Here you will see that the silting in the channels are not considered. We are not going to consider the silting properties of the channel. That is further a higher level course, especially on sediment transport and all. We are only going to see partial scour in the channels, that will be followed, how the partial scouring and all occurs. So, and how you can design channels for such erodible conditions and all, that we will see. Grassed channels, the channels on which the beds and sides consist of grass surfaces, they are called grassed channels. You will see they have different properties compared to other non-erodible channels and all. You will see there is a quite difference there, especially in the roughness aspect and all. Grass offers much resistance to the flow, and you will see the roughness coefficient considerably different in this case. The non-erodible channels. So, most of the lined channels, most of the channels which are lined, for example, if you have any arbitrary cross section of the channel, if this is the channel bed, and if you line the channel bed with some material, such channels are called lined channels. So, they allow, means they won't allow, will not allow seepage or will not allow scouring along the bed. Along the bed it will not allow. So, such line channels are generally called non-erodible channels. For designing non-erodible channels, what do the designer do? A designer, he has to first compute the dimensions of the channel using uniform flow formula. So, once say if he has computed the dimensions, he has suggested, he got the area of the flow, he is then subsequently understood, means subsequently he suggested the depth of flow and all. Based on that, one can design decide the dimension of the channel, what type of channel is to be incorporated, or for the amount of flow, what is the amount for the given amount of flow, what is the depth and all required and all. He can compute it using the uniform flow approximations. This you have already seen how to compute uniform flow and all. Then the suitable dimensions, they are adopted after suggesting say certain dimensions, then the suitable dimensions among them, we will adopt it as per the hydraulic efficiency of the channel, say hydraulic efficiency, or you can also use some other efficiency criteria or empirical relationship, or you can also see whether it is economical or viable to use certain dimensions of the channel, whether it is practical or not. You may see some of the most hydraulically efficient channels may not be able to be incorporated in the ground level. You cannot construct such type of channel, it may be quite possible. Then there is no point in designing such type of channels. So, you have to see various practical conditions and all, whether it is economically feasible or not. What are the factors to be considered by designing of non-erodible channels? Of course, when you design the channels, especially the non-erodible channels, you have to consider some of the factors. The first one, as it is being suggested here, the kind of materials. So, what is the material you are going to use to construct the channel? That is quite essential, because it is the material that determine the roughness of the channel, right. You are quite aware now, because different materials have different type of roughness coefficient, and once the roughness coefficient changes, the flow or the discharge changes quite immensely. So, it is one of the most important aspect while designing the non-erodible channels. You also need to consider the minimum permissible velocity. Why the minimum permissible velocity, and why not the maximum permissible velocity? As mentioned, this title is Design of Non-Erodible Channels. So, the non-erodible channels, we are suggesting that the bed of the channels, it is not getting eroded, or even the side banks, the side of the channels, they are not getting eroded. So, usually the amount of suspended material in the water, they are negligible. You can consider it as negligible, or there is no erosion of the bed. So, definitely the maximum permissible velocity is not coming into picture. It is the maximum permissible velocity or the maximum velocity that determines how much amount of scouring will take place and all in a given bed. So, people who are interested to do sediment transport analysis and all, or interested to undergo courses on sediment transport, or whoever are doing them, they will be quite aware of this fact that the velocity of the water is quite important in determining the scouring, how much amount of scour takes place and all. In our case here, we are suggesting the minimum permissible velocity for non-erodible channels. This is to avoid, if at all any suspended materials are there, we have to avoid that thing, and also to avoid growth of aquatic plants and all. Then the another factor that is quite important in designing of the channels are non-erodible channels are the channel bottom slope and the channel side slope. Next important criteria is the freeboard. What do you mean by freeboard? The amount of, okay, we will discuss it in an expanded way. The amount of height means free height, whichever you are going to give beyond the normal depth of the flow for the given design, that is called freeboard. We will discuss that definitely. Also, you need to consider the efficiency of the cross section. Whichever design you have done, you have to see whether it is hydraulically efficient, or whether it is empirically efficient, whether it is economically efficient. All those things you need to take into criteria. So, like these factors, we will just slowly discuss each of these factors and see how the design of channels can be done. The non-erodible materials used for lining in channels. As we mentioned here, for the various factors to be considered in design of non-erodible channels, the first criteria we suggested, or the first factor we suggested, is the kind of materials that are to be used in forming or in designing the using the development in developing the channel body and all. So, what are the different materials that are used for lining the channels? Concrete, as you know, concrete, it is quite strong and it does not erode that much. So, concrete is generally used in many of the channels, cross sections and all, to as a lining material. Next one is stone. There are various rocky stones and all, or stone masonry, where the stones are much stronger and also it avoid erosion of the bed and sides. So, stone masonry is also quite done for the lining of the channels. You can also use steel, or you can also use cast iron, various materials like that do not erode in water. Can also use timber, a good seasoned timber is quite resistant to erosion and it also will be carrying enough amount of water. So, timber is also quite used in lining of the channels. Glass materials are also used for the lining of the channels. People have also used PVC, or they have also used perspex sheets. They are also used some other type of plastics etc., as lining materials in channels. So, there are not only this much, there are many other materials which you may be quite aware also, which I have not discussed here. So, you can refer many other books related to lining of channels and all. So, there you will be getting better picture. As you have seen, there are various materials that can be used for lining of the channels. So, how do you select a certain material, or what are the criteria for selecting a certain material? Definitely, the availability of the material plays a very strong role in adopting that material as the lining material for the given channel. If, for example, if it is a slightly hilly area where a certain type of rock is very much available, that rock can be readily used as a lining material in the channel passing through that region. It is cost efficient also. The cost involved in incorporating that particular lining material in the channel, whether the cost is getting escalated considerably if you line the channel with a certain type of material, whether the cost is getting escalated or not, depends on that. If it is economically viable, adopt that material. The method of construction of that channel, for various type of constructions, say if you require, means what is the method of construction. Certain contractors may be having different type of materials available with them to construct a certain sections or certain works and all. Certain other contractors may be having another type of materials. So, it depends on all those things. So, you cannot say that only this so and so material has to be used always for the channel construction and all. So, various things are the method of construction. What are the different methodology for construction? One can use pre-stressed concrete, one can use already available fabricated concrete that are already fabricated somewhere else, and you can just incorporate that lining material in the location, or one can fabricate in the location. So, all these things means a different picture, it will give a different picture. Now, what are the purpose of the channel? Say, what is this channel for? Whether it is for carrying pure potable water, or whether it is for carrying irrigated water, whether it is for a hydraulic project, whether it is for carrying waste water, or whether it is for some other type of waste or whatever things that are coming into your picture, depends on various purposes. So, you have to adopt the materials as per. If it is a waste carrying channel, definitely if you use timber or if you use steel and all, you may see that steel may react with the various chemicals in the waste and your channel may get eroded or something else, means erosion, this is chemical erosion and all that may occur there. So, you have to avoid such thing. So, as I asked you earlier, what is the purpose of lining? Now, in between this lecture, why I need to pose you this question? Because again to reiterate in front of you, that is the purpose of lining of the channel is, as this is the design of non-erodible channels, you have to line the channels, and this lining is done to prevent erosion of the bed as well as the side and to prevent the seepage of water into the channels. So, if you have such a channel, this thing, you may see that the beds here, it may get eroded due to the flow of water. So, if it starts getting loosened, then the lining is not proper. So, if a proper lining material is incorporated, the loosening of the soil can be avoided. Also, if any water is infiltrating or seeping into the soil, and if you see that the loss of water due to that such type of seepage, if it is quite high, then you can avoid seepage by proper lining of the channel. So, the next factor which we suggested while designing of the non-erodible channels were minimum permissible velocity, if you recall that, minimum permissible velocity. Now, I would like to ask you, what is meant by minimum permissible velocity and what is the requirement for minimum permissible velocity? We had already hinted earlier, the minimum uniform flow velocity that has to be maintained in the channel to prevent sedimentation and siltation. This is called the minimum permissible velocity for the designed channel, non-erodible channel. For the designed non-erodible channel, a minimum uniform flow velocity has to be maintained. Otherwise, whatever suspended materials are there already there in the channel, that may start getting sedimented, deposited. So, you have to avoid that deposition. Also, if you see that if the velocity of flow of water in the channel, if it is too slow, there are chances of plants, aquatic plants growing in the channel. So, you need to avoid, means you have to keep a certain from the velocity, so that the aquatic plants are not grown. You will also see that as this is a non-erodible channel, most of the cases the sediments or the suspended materials present in the channel are negligible. Then you need to design you give the minimum permissible velocity based on the growth of aquatic plants. For many cases, it has been observed that approximately around 0.80 meter per second velocity of flow. If you keep the velocity of flow approximately around this thing, means not less than 0.8 meter per second, most of the aquatic plants that are present, that means that are not allowed to grow, means it will avoid the growth of most of the aquatic plants around at least around this velocity. So, you have to keep the velocity we design at least to be greater than or equal to 0.8 meter per second. The next factor we suggested while in the design of the channels are the channel slopes. So, what are the channel slopes that are present? For any channel, there are bed slope and side slope. You know what is meant by bed slope. Say if the channel is like this, if it is carrying water, uniform flow depth, this is the longitudinal view, flow is occurring. Then the slope of the bed, this is called bed slope. The slope of the sides of the channel as given here, that is called side slope. So, the bed slope, it is determined by the topography of the region, mostly the topography is the region, as well as the energy head required for flow of water. You know that means based on means you require the water flows, especially in open channel flows, water always flows from higher energy to lower energy. So, when you compute the energy head, you need to see that the energy head at the upstream is always greater, then only it can flow to the downstream. So, you have to design it appropriately. So, bed slope needs such criteria, and also the topography plays a quite important role, various way. The bed slope also depends on various purposes. Say for example, if there are multiple projects, irrigation projects or hydraulic power projects, if such projects are there, you will see that the channel, the water at the entry of the channels here in the channels for irrigation purpose as well as the hydraulic power projects and all, at the entry of the channel, it should be at quite higher elevation. If it has to be at higher elevation, what do you mean by that? Then the feeding or whichever channel is feeding to these channels, they need to be at a higher elevation. So, in those channels the bed elevation also need to be kept at a higher level, so that you will be able to feed water properly for the irrigation projects, hydraulic power projects and all. In most of the cases you use mild slopes. In such situation, mild slope channels are used or negligible slope channels are used. So, in the channel slopes we suggested that the channel side slopes are also quite important. The channel side slopes, it depends on the various kinds of materials. You have seen that you can use different types of materials for construction of channels. So, based on the materials, one may have to adopt the side slopes. Say here in the side slope, what should be this ratio 1:b? This ratio 1:b of the side slope. If it is a rock, you will see that you can almost keep the channel cross section or the channel side slopes as vertical. If it is a very loose soil, a loose sand soil, you may not be able to keep it in a vertical, then you may have to give some side slopes. So, there are different based on different materials and different these things. Also based on the method of construction, you have to design the channel side slope. You also need to see whether the seepage losses you have to minimize or whether you are allowing certain seepage losses, so that the general area in the region is getting recharged. Also you need to see the climatic changes. All these factors, all these things depends on determining the channel side slope. So, usually steeper side slopes are given to make channel more efficient. You will see later also today, we will discuss them later. If the side slopes are steeper, that channel is able to carry more water compared to shallow or what you say non-steeper side slope channels. So, those things also come into picture. What is the criteria of the general social criteria, that is also required. A table we have just given for suitable side slopes that are generally adopted. So, in rocks it is 1:1.25 or almost you can say 1:0 also can be given. Means there is no need of side this thing. For stiff clay with concrete lining, you will see that this is 1:0.5 up to 1:1. So, let me draw the thing here. So, your 1:B, this is the thing suggesting the thing. So, for stiff clay, this 1:B is almost 1:1. For loose sandy earth, this is 1:2. For sandy loam or porous clay, this is 1:3. So, based on materials, as we mentioned earlier, you have to adopt the side slope, or if you try to incorporate 1:1 for a sandy loam, this thing, you will see that the side slopes will get collapsed and your channel gets broke, means it gets failed. So, you cannot construct such type of channels. So, you have to see the material that is being adopted for channel design. The next design factor while designing the non-erodible channels mentioned was freeboard. What is meant by freeboard? Just consider a channel section. In the channel cross section, you have designed, means using the various design parameters, you had designed that, say, the depth of flow yn should be so and so. Then you suggested that the area of flow should be so and so. Once you have designed all those parameters, the depth of flow yn is incorporated. Then while constructing the channel, you need to give further space, further vertical space. You have to incorporate further vertical space, that is, you have to extend this side slope further to a particular height, and this height is called freeboard. Means if your designed height for the discharge, uniform discharge is yn, then yn plus certain freeboard height also need to be given. That has to be incorporated while you design or while you construct the channel. Why this freeboard is given? Why it is required? Because there are chances that the water may spill from the channel due to certain fluctuations and all. So, you do not want to allow spilling of water. So, therefore, you need to provide freeboard. Freeboards are very essential when you construct aqueducts, say aqueducts that carry water from one level to another level and all. If there is a spilling of water, it can cause huge loss and all. In laboratory flumes or even in waste water carrying channels or waste material carrying channels and all, you will see that if any spilling of the quantity occurs, that may hamper the environment or that may cause the loss of material and all. So, you need to provide sufficient freeboard or sufficient height while designing the channel, or you have to construct the channel in such a way that certain free distance, vertical distance is given. So, freeboards are provided to counter water depth fluctuations due to waves, wind, tides, etc. Yes, of course, for unforeseen circumstances, as you have witnessed in Japan recently due to that tsunami and all. For such situations, you cannot design the channels. So, there the nature, it depends on the nature. Usually, the freeboards are applied up to 5 to 30% in most of the uniform flow. Most of the channels you can design from 5% to 30%. So, this height is around 5 to 30% of the normal depth of the designed channel. So, that is sufficient in most of the cases. So, the next portion which we are going to discuss is the best hydraulic section. So, what is meant by best hydraulic section? If you recall the term conveyance, I hope you recall them. Conveyance K for uniform flow, it was given as according to Manning, from the Manning's equation, 1 by n A r to the power of 2 by 3, where your n is Manning's coefficient, roughness coefficient, A is area, of cross section, r is your hydraulic radius. So, for such a section, for any section, so the conveyance you had already been taught of, and you know what is the specialty of conveyance. So, if conveyance for a given discharge, if it is more, then do not you think that that section is able to convey more water, or it is able to efficiently carry more water compared to some other type of sections. So, that means, if your conveyance is high, that can give, if your conveyance is high for a given discharge, then that can give a better efficient cross section of the channel. So, how can you suggest those things? So, for your conveyance factor K is equal to 1 by n A r to the power of 2 by 3, this is 1 by n A to the power of 5 by 3 P to the power of 2 by 3. Fine. So, whatever wetted perimeter you have, for the cross section, you are seeing that the conveyance is inversely proportional to P to the power of 2 by 3. So, if your wetted perimeter, if it is less, if wetted perimeter is less, then K is more, your conveyance is more. So, hydraulically, so in terms of hydraulics or hydraulically, less wetted perimeter conveys more water. Fine. So, you can say that the sections having least wetted perimeter, such sections are called sections having least wetted perimeters, they are called best hydraulic sections. Okay. So, you have seen various type of channels, say triangular, you have seen trapezoidal, you have seen rectangular, also you have although we have not discussed much on this thing, semicircular channels. So, you have seen such channels, right. Now, there is no need for me to further, you know that for such triangular channels your area is, so we have seen for earlier also in our various parts of the courses, this in the triangular section you know what is the area is equal to, say for such given this thing, if side slope is 1:b, then you can give your area as A is equal to b y square, your wetted perimeter P is equal to 2y root of 1 plus b square, right. In the trapezoidal section you have seen area A is nothing but it is equal to, say if the bottom width of the trapezoidal channel, if it is equal to b 0. So, we are following the same convention. So, b 0 plus and the side slope if it is 1:b, b y n, your wetted perimeter P, this is equal to b 0 plus 2 y n root of 1 plus b square. In the rectangular section you have already seen that earlier also, your area is equal to b 0 y n, your wetted perimeter P is equal to, yes, 2 y n plus b 0. Now, for a semicircular case we have not discussed like that, but still it is quite obvious for you. Your wetted perimeter here, this is equal to pi times y n, and your area is equal to pi by 2 y n square. So, you have the following quantities. So, as we mentioned, the hydraulically best cross section of the channel is the one that is having least wetted perimeter. So, among these channels itself, now seeing the various formula, seeing your various formula, you have seen these formulae. Say for any given area, for any given, if you just give, if you from your design you have already suggested that the area of flow should be so and so value, and if that area is given, then if you want to find the hydraulically efficient cross section, then you know that for the given area, semicircle is the one that is having least wetted perimeter for any given area A. If say if A is equal to same here, here, here and here, then the least wetted perimeter case will be observed in semicircle. That you can just work it out also, you can use your normal differentiation and just see that. So, semicircle is having, semicircle gives least wetted perimeter for any area A given to you. Then you can adopt semicircular channels and all, but of course, you will see that to construct semicircular channels and all, it may not be that much cost efficient and all, but theoretically or hydraulically through the mathematical computation it is observed semicircle gives you the least wetted perimeter for any given area. Now, the question or what we want to suggest is that if the slope of channel, that is S 0, roughness coefficient area of flow If these three are already given to you, or if it has been already determined through other processes, now the next purpose for you is to find the dimensions that has to follow the efficiency criteria. And we suggested that a minimum wetted perimeter section will be having the most efficiency in the conveyance of the discharge. So, the conveyance of flow or the uniform flow, the conveyance will be maximum for least wetted perimeter sections. So, you have to see that if there are some restrictions, say you cannot construct, you have to definitely construct, say restrictions like specific shape of the cross section that has to be maintained. For example, some criteria from any organization who is developing that project and all, any funding agency or any requirement from the locality and all, it suggests that you have to have a rectangular cross sectional channel for carrying the water from this location to that location. If such a criteria is there, then how will you suggest the most economical rectangular cross section? For example, rectangular cross section is a must. If it is a must, then hydraulically efficient rectangular channel has to be determined. How will you determine that? You know the wetted perimeter P for rectangular channel is B 0. For rectangular channel it is this thing. So, you require a wetted perimeter that is having least property, means the wetted perimeter is least. So, according to the differentiation rule, I am just differentiating dP by dy to get a minimum value. It has to be dP by dy has to be equal to 0. Now, you are already suggesting the area of flow equal to A is given, right. You already know A is equal to B y n, B 0 y n, and now this is a constant. If A is equal to B 0 y n equal to constant, that means your B 0 is nothing but A by y n. Therefore, dP by dy equal to 0 means d by dy of B 0 plus 2 y n. This is d by dy of A by y n plus 2 y n. What is this quantity? A is a constant. We suggested A all through design, already A has been established, A is a constant. So, it is not going to vary. So, this quantity is minus A by y squared plus 2, and it has to be equated to 0. Therefore, your most efficient cross section, it can be obtained either directly from this, or you can suggest that you can use the thing here now. A by y squared is equal to 2, that criteria can be used now. you will see you incorporate the quantity here in this equation, you incorporate it in this equation, this relationship. Of course, this is your normal slope. So, you have seen this relationship, you incorporate this relationship as mentioned in this particular case. So, you will see that you will get or V 0 y n into E by 2 is equal to y n E whole square, or it suggests that so this is the criteria for the most efficient hydraulic efficient or the hydraulically efficient rectangular cross section. That is, your depth of flow should be half of the width of the channel. So, that is the criteria. So, here the suffix E is showing the hydraulically efficient channel. So, for rectangular channel one can prepare it like that. Now, as an exercise, let us develop hydraulically efficient channel section for trapezoidal shape. So, if the local region, if it demands that the channel cross section has to be, it has to be trapezoidal in nature, its shape has to be, the cross sectional shape has to be trapezoidal, then what is the hydraulically efficient channel cross section? So, here again the bottom width is B 0, side slope is 1:B, normal depth is y n. Then you use the same criteria, you know A is equal to B 0 plus B into y n by into y n. We are wetted perimeter P is equal to B 0 plus 2 times y n into root of 1 plus B square. To obtain the hydraulically efficient cross section, your dP by dy should be equal to 0. That means, d by dy of B 0 plus 2 y n root of 1 plus B square. Now, what is B 0? You already know from this particular equation, you will see that area of cross section is equal to constant therefore, B 0 is equal to A by y n minus B y n. So, you substitute this quantity there in the relationship dP by dy equal to 0. You substitute for B naught, the criteria given now develop. So, d by dy of A by y n minus B times y n plus twice y n root of 1 plus B square. So, this is equal to 0, as you know that. Differentiate the quantity, you will get minus A y n squared minus B plus 2 times root of 1 plus B squared. This is equal to 0. So, you are getting A is equal to 2 times root of 1 plus B squared minus B, the whole quantity into y n square. So, for a hydraulically efficient cross section, your area, if it is given to you, that it can be given in the following relationship using your normal depth, it can be obtained in the following form. So, now this quantity as mentioned earlier, it is already given to you. So, you substitute this relationship now for B 0. So, your B 0 is equal to 2y root of 1 plus B squared minus B y n squared by y n minus B y n. Therefore, rearrange the terms, cancel off the terms whichever is obvious to you. So, this thing and this thing can be cancelled off. Like that, you will see that you are going to get B 0 is equal to 2y y n into root of 1 plus B squared minus B. Okay. Or you can also see that for the hydraulically efficient channel cross section, the normal depth should be equal to B 0 by twice root of 1 plus B squared minus B. So, this relationship has to be followed. So, you can use this thing. As seen in the rectangular cross section, the hydraulically efficient cross section, the depth of the normal flow should be equal to the half of the width of the channel. Similarly, here this is B 0 by 2 into certain quantity root of 1 plus B squared minus B. Again, we can see a problem. Maybe as a quiz I can ask to you. I can ask as a quiz to you, show that the best hydraulic trapezoidal section is the one that is half of a hexagon. You know, hexagon is a regular shape. So, I want you to prove that the best hydraulic trapezoidal section is half of a hexagon. You know what is hexagon? It has all the sides equal. It is a regular shape, it has all the sides equal, say B, something like that you can say. Now, I asked you that the best hydraulic trapezoidal section is the one that is half of a hexagon. So, this particular section, this portion, whatever is there, that is the best hydraulic trapezoidal section. How can you prove that? You have already seen what is the criteria for the best trapezoidal section. You can develop from there itself how that the best hydraulic trapezoidal section is the half of a hexagon. It can be proved. Just do that. Okay, the solution for this particular problem as suggested. So, this is the trapezoidal section. We have asked you, means we have already seen that for hydraulically efficient section, your B naught or the channel bottom width should be equal to twice the normal depth into root of 1 plus B squared minus B. Now, the requirement here is what should be the channel side slope B. That is a requirement. If you are able to identify what is the channel side slope B based on this given criteria, you can easily find that the channel side means the channel or the hydraulically efficient channel section for a trapezoidal shape is nothing but a half of an hexagon. Let us see how that is thing. Your wetted perimeter here again, it has to be differentiated with the channel slope, channel side slope, and you have to see that that is the minimum one. So, if you equate it dP by dB equal to 0, what will you get? You know what is P? P is equal to B 0 plus 2 y n root of 1 plus b square. So, you differentiate that, what will you get? So, the criteria dP by dP equal to 0, that you require that. Now, you have P is equal to B 0 plus 2 y n root of 1 plus b square, and B 0 is equal to 2 y n root of 1 plus b squared minus b. So, in this case you have to d by dB of like this, you need to determine the quantity. So, what is this differentiation? I have worked it out and I got the thing as, I got it around, say this 0 is equal to, on simplifying, 1 plus, you can do it on your own, 1 plus b squared to the power of minus half b, this is twice minus 1 equal to 0, or b by root of 1 plus b squared is equal to half. So, you know, for the side slope, we are talking about the side slope of the channel, 1 is to b. So, root of 1 plus b squared, it indicates your hypotenuse of this portion. So, what does this mean? So, this, if you note about this angle as theta, so you can easily suggest that b by root of 1 plus b squared is equal to half is equal to your sin theta. Therefore, what is theta? It is quite obvious to you. So, I am not going to discuss further. So, if this is so and so value, it is now quite confirmed the best trapezoidal section, hydraulically efficient section will be the half of a hexagon. Thank you.